Previously, on Engineering Jigsaw, we've talked a lot about how modern vehicles rely on software. We've talked about how ECUs or HPCs containing hardware such as microcontrollers or microprocessors are linked by networks in vehicles to allow software to share information. We've also covered how flash bootloaders, unified diagnostic services, and SOVD permit ECU software to be updated. How is the software created though? Let's go find out. Hi everybody, I'm Ian Cunningham from VectorGB. Welcome to this foundation level episode of Engineering the Jigsaw, How is Embedded Software Developed? Foundation episode number 24. As a recap, way back in episode F2, we first talked about embedded software and how it works with the hardware of an ECU within an embedded system to provide control via logic or rules and calculations in the context of control engineering. And of course, in control engineering, we're aiming to achieve a desired level of performance. In episode F9, we talked a bit more about that desired performance. So we talked about hard real-time control, which means that we're operating with very strict timing requirements or deadlines in terms of when outputs must be activated after inputs becoming in a certain state or set of states. And we call this hard real-time control. And if we achieve hard real-time control, we achieve deterministic or predictable performance. What does this mean for the kinds of software we could use in ECUs though? Well, if we're thinking about software, there are two fundamental kinds of software we can choose between. Will it be compiled or will it be interpreted? Let's go and have a quick look at what these terms mean before we go into which one we typically use to achieve hard real-time performance. In the case of interpreted software, interpreted means we need an interpreter to run the software. That sounds a bit like a tautology, but you may well know interpreted software. So if you use Python, JavaScript, or Scratch, these are typically interpreted languages that are used in software development. The advantages of using an interpreter is that it's easy to see the effect of a change. You can change your software and run it again immediately, which is great if you're doing prototyping. The disadvantages, though, are that you need this extra software to be able to run the software you want to run. So we kind of have this kind of dependency to extra software. Also, typically, not always, but typically, interpreted software tends to run more slowly and more unpredictably due to the extra software that's involved. And also, the interpreter actually runs a process before it runs the software every single time. So it actually kind of compiles the software every time it's run. So we have this kind of process of compilation happening every time, which can be wasteful, let's say, in terms of execution time. So let's think about compiled software. So compiled software is able to run natively as machine code. What that means is we have an offline compilation process where we use software to perform the building of the software, and then we can take that and we can put it to where we want to run it, such as a microcontroller. And when we run the software, it just runs. We don't have to go through that process of compiling the software every single time. So the advantages of this are clearly it runs directly on the hardware, the microcontroller or microprocessor. This is what native means, and it is able to run quickly. And also you can, with compiled software, achieve predictable or deterministic behavior. You can also not achieve it, but it is possible to achieve it. That's the main thing. The disadvantages, of course, is that the main disadvantage is that you have to do this compilation process offline before you can take your software and run it where you want to run it, which can take some time. And the advantages for hard real-time control far outweigh the disadvantages, so we tend to use compiled software in embedded systems. I should mention here some typical kinds of compiled software you might encounter are C, C++, Rust, also Java, Kotlin, Go. There are many compiled software kinds out there. And I should really quickly mention that you may know Java or Kotlin for mobile app development, but these are typically run with some extra software called the Java Virtual Machine, or JVM for short. And this dependency on extra software, again, is something that we don't really necessarily want to have in embedded systems. So we typically are not using Java or Kotlin in hard real-time embedded systems, again, for that reason. So how does compiled software development work? Let's use the example of C. So we write some C source code in a file with a .c extension, as we see here. We've got just a few lines of source code. And this is like the classic hello world program that you may have encountered in other languages if you've done any programming at all. So firstly, we're including a library, a standard I/O library that allows us to do I/O tasks. We then have a declaration of a function main, and it has no parameters. It's returning an integer, is what the int means at the start. Then we can see we're printing the words hello world, and then we are returning or exiting and returning the value 0. So we've written some software. It could also be generated, perhaps. Probably not for this trivial code, but for more complex code, we can generate C as well out of models or model-based tooling. So what happens to our C file? Well, what happens when we click the build button in our software development environment is it's actually put through some special software called a preprocessor. The preprocessor creates an intermediate file from the source code. In this intermediate file, amongst other things, any macros that we've used are expanded. So kind of shorthand we've put in is kind of expanded to be like the long form. Also, comments are removed. And then the intermediate file is compiled to assembly code or assembly. And we can see an example of assembly with the .asm extension on the screen now. You can see this is substantially less readable than the C file we were looking at previously. So C is a mid-level language. Assembly is low-level, referred to as low-level. Assembly, each line here corresponds to an instruction that we want our microcontroller or microprocessor to do. So we're really at the level of what the microprocessor needs to do. So there's a lot of individual things that need to happen to put that string on the screen. Where do we go next? We've got assembly. We need object code. So we take our assembly code and we assemble it into object code. And this is a binary representation of the memory content of the microcontroller or microprocessor. Strictly, this is relocatable object code, and that's because some parts are missing, such as memory information and some libraries. So we need to put them in, and that's the next step. We have another piece of software which is called a linker, and this creates the final machine code that will run on our hardware. So now we have a .bin binary extension. Sometimes it's hex. There are other kinds as well. And of course, at this point, if all has gone well, we're going to have working software. So let's think about the software lifecycle. We've talked about the development and how that software is built into something that we can put onto a microcontroller. What happens next? Well, we don't necessarily know that our software works correctly. So we want to test it. So after we do development, or while we're doing development, we will test our software, but we will test it extensively before we go near an embedded system with software. So we do a lot of testing during development, but we also do additional testing before we kind of let our software loose in the wild with real people, real users that could possibly be hurt if our software goes wrong. So after testing it, we can deliver that software to make the software release available. And then we can deploy that software, which means that it's running and installed and running, to get the words in the right order. So this is a simplified software lifecycle: develop, test, deliver, deploy. Of course, in a real software project, we're typically not a single developer. So what we do is we have to take the work of many developers and we have to integrate it. So we have this integration step that we see here. So we're typically, somebody has the job of trying to take everyone's stuff and make one thing out of it that can be built and then tested, delivered, deployed. Great. Let's start to automate this because it sounds like a lot of work. Obviously, in an embedded system, we will have some kind of device at the end, not a person. So there's our first step. And of course, if we're in a vehicle context, we are running our software on ECUs, and we may have the ability to make use of over-the-air technology, such as SOVD, to help us deploy software automatically. So we can start to kind of think about automation quite readily when we think about over-the-air software technology in terms of the deployment of software. But as I said, we've got lots of manual work at the start. Integration and testing can be very manual. We should be trying to make things easier there. We can automate throughout the software lifecycle. So integration, test, and delivery may be automated as well. Automated integration allows something called continuous integration. And what this means is that developers make small changes and send their changes continuously to an automated process that will automatically integrate them, and along with changes from other developers, and compile the software to make it available for testing. Of course, we also probably want to automate our testing as much as we can. And this allows us to have continuous testing alongside our continuous integration. And continuous testing really allows us to get very fast feedback to our developers on how good their changes are or their new code is. And it also allows our developers to really focus on writing software, as well as permitting testers to focus on creating new tests to improve quality or to test new things that are coming in. So we're not spending lots of time kind of repeating work that we've done before. We're trying to remove repetition as much as we can. And combining CI and CT is a very common first step in the software lifecycle. Beyond this, we may want to consider automated delivery. So as soon as we've tested something and we've proved to ourselves that it is ready for release, we can deliver it. So, and again, here we could do this continuously. So if an integrated change gets through testing, we can automatically deliver that software ready for use. And of course, we can automate deployment as well, to have continuous deployment, CD. So really important. We've got 2 CDs now. So first point, make sure you understand which CD you're talking about when you talk about CD. Is it continuous delivery or is it continuous deployment? Because we don't always want to deliver software, deploy software immediately to embedded systems because of the safety relevance that we sometimes have. So sometimes we'll hold back releases until we're able to perform certification activities. So really important that when you talk about CI/CD in embedded software, you understand whether it's continuous delivery or continuous deployment that you're talking about. And this overall automated environment is called a CI/CD pipeline. And it's very common to have many pipelines running either in series or in parallel to match the needs of different software lifecycles. Often we'll have parallel pipelines focused on CI and some pipelines that then run in series, and then we have what are called staging points in between them. So there's kind of an architecture where we kind of funnel into a single thing at the end, but possibly from quite a wide starting point. Anyway, pipeline architecture is a whole other topic. So on the subject of other topics, what next? What else do modern software projects need? Well, you're going to have to join us next time to find out, because we're out of time. So as a summary, embedded software is typically compiled and exhibits deterministic or predictable behavior. The compiled software should be tested before being delivered and deployed. Really important. Please don't forget to test your software before you deliver it and deploy it. Embedded software processes can be automated, which allows us to have continuous integration, potentially achieve continuous testing, continuous delivery, continuous deployment. Remember the 2 CDs as well. CI/CD pipeline then refers to an automated software lifecycle, and pipelines may be configured to run in parallel and in series in a particular organization. If you want to know more about pipelines in the context of developing software, please visit our website or contact us for Vector's tools, services, and training that are relevant to creating embedded software pipelines. And join us next time to find out the role that pipelines and automation play in something called the software factory. If you want to get in touch with us in the meantime, join me after the music. Really hope you've enjoyed this episode of Engineering the Jigsaw. Make sure you give it a thumbs up in YouTube. If you have questions or ideas, then give us a comment down below the video. If you don't want to do it in public, if you want to keep it private, then drop us an email to our special email address, engineering.jigsaw@vector.com. You can find a link to our webpage with those contact details on in the description for this video. Make sure that you subscribe to get notified as we release new episodes and as Vector publishes its excellent and informative videos on its YouTube channel. Make sure to check out our playlists. We have our foundation episodes playlist and also intermediate level playlist as well for you to binge and catch up with. We'll catch you for another episode soon. Goodbye.